Thanks so much for braving the weather and the parking spaces and for joining us at the 21st Annual Presidential Lectureship. We're so excited. Phil has organized a wonderful afternoon for us, and we're going to start with some pure joy. Rachel Josselson and Uri Tsakor are going to entertain us to begin with. Please.
Translation synopsis of each piece so that you can get more out of it. The first piece is Auf eine Burg within the grounds of a castle. The old knight has fallen asleep at his lookout post up there. Over there rain showers pass and the forest rustles through the railing. His beard and hair have taken root. His breastplate and ruff have turned to stone, and he has sat up there in his quiet hermitage for hundreds and hundreds of years. Outside it is quiet and peaceful. Everyone has gone down to the valley. Solitary forest birds sing in the empty window arches. A wedding party is sailing down there in the sunshine on the Rhine. Musicians are playing merrily, and the beautiful bride, she is weeping. And yet it is so far from here. As if my sweetheart must be waiting for me in the garden, full of red and white and yet she has been dead so long, and yet she has been dead so long.
Ich höre die Bächlein rauschen im Walde her und hin, im Walde in den Rauschen, ich weiß nicht, wo ich bin. Die Nachtigallen schlagen hier in der Einsamkeit, ich wollte sie was sagen von der alten schönen Zeit. Im Mondschimmer fliegen, als seh ich unter mir, verschlossen Tage liegen, und ist doch so weit von hier, als müsste jede Note von Rosen weiß und rot meine Liebste auf mich warten, und ist doch so lange tot, und ist doch lange tot, und ist doch lange tot.
Next is Swedish, or twilight. Dusk is about to spread its wings. The trees quiver in alarm. Clouds pass overhead like heavy dreams. What is the meaning of this terror? If you have a deer you love above all others, don't let it graze alone. Huntsmen roam in the forest, blowing their horn. Voices wander back and forth. If you have a friend here on the earth, don't trust him now. He may show friendship with his eyes and mouth, but he is planning war during this insidious peace. That which sinks in weariness today rises newborn tomorrow. Many things are lost in night. Be on your guard, be watchful and alert. that we'll be singing today, as well as the final song of this cycle, is called Frühlingsnacht, or Spring Night. Over the garden, through the air, I heard migratory birds passing. That is a sign of spring fragrance. Down there, blossoms are already appearing. I feel like exulting. I feel like weeping. It seems to me that it just can't be. All miracles are once more shining in along with the moonlight. And the moon, the stars say it, and the rustling grove whispers in its dreams, and the nightingales sing it. She is yours, she is yours. This is actually a cycle that's mostly sung by men. So I decided to do it anyway.
Rachel and Uri, thank you so much. We're graced by your presence on the campus always, and so pleased to have you here today. Speaking of being graced, we really have a treat in store for us today. It's my great honor to welcome you again to the 21st Annual Presidential Lecture. President James Friedman established the Presidential Lecture Series over 2 decades ago, and the event not only showcases some of the outstanding faculty members in the university, but it also serves to encourage communication across disciplines, President Friedman's main idea. It brings the tremendous work of our faculty scholars to each other and to the general public in our wonderful community. For 21 years, through this forum, we have proudly shared our excellence in areas ranging from history to literature to the health sciences to law, to physics and astronomy. And I'm delighted today to introduce you now to our 21st presidential lecturer, Phil Kutzko from the College of Liberal Arts and Sciences. He's a collegiate fellow and professor of mathematics. Your program outlines many of Phil's career accomplishments. It's clear that he's an excellent scholar, which his lecture today will demonstrate and affirm. But Phil's biography does not fully capture the depths of excellence in his teaching and his service. He is truly a master teacher, and many of you in the university know that last year he received the Philip G. Hubbard Award for Outstanding Education. Perhaps an even better barometer of his teaching excellence is the applause that often greets him when he enters a classroom before his lecture. Phil is a consummate university citizen as his tireless efforts in expanding minority graduate education at the UI and in his field attest. As a scholar, Phil exhibits care and passion, and those essential characteristics of the best professors extend into his teaching and service as well. Generations of students remember Phil Kutzko as a person who mattered, and mattered greatly in their lives. In the letter that forwarded Phil's nomination for the Hubbard Award last year, Dean of the College of Liberal Arts and Sciences, Linda Maxon, noted Phil's status as, quote, a master teacher across course levels, and his particular ability at helping students overcome their anxieties about the ability to do math, end of quote. Let me also share with you some very brief comments from student testimonials for that award. Quote, Professor Kutzko entered each morning with a smile on his face He wanted to teach, and we knew he wanted to. Every question he phrased in ways that either made us laugh or put it in terms for the average freshman to comprehend. The one thing I remember so well about Professor Kutzko is when I entered class with him one day, I said hello, and all I was looking for was a hello back. He took his time, however, to stop and find out how I was doing and if everything was clear. This was the first time a professor took time out of his busy schedule to talk to me, end of quote. Another student tells of Phil's willingness to spend several hours per week helping the undergraduates one-on-one. Quote, he once told me that to build a mansion, you must have a great foundation, and linear algebra in mathematics is that foundation. We'll take your word for that, Phil. His ability to communicate with his students one-on-one in a way that motivates and inspires us to rise to a challenge and overcome that challenge is phenomenal. End of quote. Another quote, Phil has been very concerned about how I am doing outside of my academic life as a PhD student. I come from a very close-knit traditional Latino family. My parents were concerned about how I would be treated in a homogeneous area such as Iowa. When my mother came to visit Iowa for the first time, Phil invited us over for dinner at his home. After that, she knew I had arrived to the right school and that there was a person who would help me succeed in my career. Phil has the amazing ability to reach out to students, even in large lecture classes. End of quote. One of Phil's closest friends, who's also with us today, is math professor Gene Madison, who enjoys Phil's, quote, unique personality, end quote, and quick wit. Those of you who know Phil know what he's talking about. Gene recalls a time several years ago when he, Gene, drove his new car over to show it off to Phil. Looking at the shiny silver-spoked wheels, Phil said, without batting an eye, different spokes for different folks. I'm sorry, but it gets worse. Even in public situations, Phil is always at the ready with instant quips. David Manderscheid, chair of the math department, notes that during one of Phil's lectures to 400 business students, some fraternity brothers streaked through the lecture hall. Phil remained unflappable, commenting, that wasn't very impressive, was it? Phil is not always the life of the party, though. Unless you're careful, you could easily find yourself cornered with Phil and his perennial argument about whether Newton or Leibniz invented the calculus. Phil's linguistic witticisms can go beyond groaners, though. Gene Madison tells that in the early days when the math department was beginning to have some success in its efforts to diversify, Phil was asked about their goals and quickly responded, we're moving from ruralism to pluralism. Scholar, teacher, mentor, colleague, and friend, Phil Kutzko touches everyone in many ways with his many talents. I know he will touch us today with a memorable and thought-provoking lecture. It is my pleasure to introduce to you our 21st presidential lecturer, Professor Phil Kutzko.
Well, good afternoon. Before proceeding, I want to thank Professors Rachel Josephson and Uriel Satkor for providing us with such beautiful music. Let's thank them again. And of course, I'd also like to thank you all for taking time away from your usual Sunday activities to hear, after all, a talk about mathematics, and especially to thank our new university president, David Scorton, and the selection committee for permitting me the privilege of addressing you this afternoon. When President Scorton first called to ask if I would give this lecture, my first thought was that maybe the stress of the new job had gotten to him. I mean, who wants to hear a mathematician? We don't have any slides to show you. We don't have any heroes to present. We can't even properly explain the way in which we use ordinary words, like smooth or incomplete. Even the word multiplication, as you're going to see in this talk, will cause some problems. Of course, we're used to this at parties where other faculty hold forth on the Big Bang or the history of the French Revolution. We're accustomed to being greeted with, math was always my worst subject, when we tell folks what we do for a living. Early in our lives, some of us are foolish enough to reveal our enthusiasm for what we do in these conversations. When asked the question, what exactly do you work on? We say things like, although it is not well understood, P-adic groups play a more and more central role in the study of local number theory. Do you know what effect that has at a cocktail party? It is a conversational gambit that we quickly drop from our repertory. So when David asked me to give this talk, I really did have to ask myself if he was starting to lose it. And with his next words, suspicion was replaced by certainty. What he said was, and if it is possible, it would be great if you would incorporate your department's work in diversity. I knew then that I faced a real challenge. But as you know, the chance to have a captive audience for an hour is one for which I will overcome almost any kind of adversity. And so I set out to prepare a talk that would somehow incorporate mathematics with diversity. And in order to start somewhere, I started thinking about titles. The first one that came to mind was a title that my friend, or I should maybe say ex-friend after this introduction, and colleague Gene Madison and I came up with for a calculus book that we thought about writing at one point many years ago. We imagined ourselves writing a text that would appeal to folks from all cultural backgrounds, and we wanted the title to reflect this. What we came up with was Calculus, What It Is, written with no punctuation, so that folks could add punctuation to taste. The problem is that the book never got beyond what one might call a discussion stage, and this seemed to me a bad precedent. As I delved deeper into the historical aspects of what I wanted to say, the 17th century philosopher and amateur mathematician Descartes began to figure more and more prominently, as you will see. One of the things I will talk about is the frustration he seemed to feel about the work of his classical antecedents. And so, given Descartes' first name, the old 60s song, Just Walk Away Renee, suggested itself. Now, my ex-wife, who shares with the few of you in the audience who understood that joke, having passed through that same period, she loved it. But my son, who's here, David, was not enthused. And since it's he and his wife, Kim, who are the ones with the grandbaby I hope to keep on seeing, I thought maybe I should jettison that title as well. So eventually I settled on the present title, which I will explain later, and I arrived also at a kind of a plan. What I'm going to do is tell you a little bit about the history of a topic that most of us learned in high school, which is construction with ruler and compass. I will contrast the classical Greek view of this topic with the one given in Descartes' book, La Géométrie, with an eye towards understanding what it was that led to the great progress in the sciences and mathematics, and that still continues today, starting in the 17th century. I will then conclude with some thoughts about the implications of all of this for future growth, both intellectual and spiritual, in this ethnically and racially mixed country of ours as we move into the 20th century. So let me see if I can get this thing to work now. I got to hit video. I got to hit computer. Look at that. Now I got to get this thing to work. If this might... All right, now someone's going to have to show me how to get this on. It should come on. There we go. Okay, and now I got to do this. It'll take me 1 second, and we're all set, I hope. This is all new technology to all of us, I guess. There. Okay. So construction by ruler and compass, as we learned it in school, was about constructing figures, which is, that is to say, various assemblages of line segments and areas of circles and various regions in the plane. We learned, for example, as you see in this picture, that a perpendicular could be erected at a given point on a line, or that an angle could be bisected, or even that we could draw a picture of an equilateral triangle inscribed in a circle. But in Greek mathematics, construction by ruler and compass was more than a means of drawing pictures. It was, in fact, the only method the Greeks had of verifying that certain figures existed, figures that were necessary for their proofs. So, for example, if you look at the proof as it appears in Euclid of the famous Pythagorean theorem, I want you to just take a look at the picture here. You notice that the phrase is, for let there be described on BC the square EB. Let me see if I can do this. There's BC, and there is the square BE, which means this square right here. And you notice that it says, let there be described on B. And actually, there's a little reference to an earlier proposition, where in fact, and the proposition's name is actually on a given line to describe a square. So the existence of this square wasn't clear to them unless they could actually draw it. And so it was more to them than just a means of drawing things. It was a means of verifying that they had certain things that they knew about. And I should remark along those lines that, in fact, the word ruler and compass is not accurate, and I'm going to discuss this a little bit because it suggests a mechanical construction. The Greeks actually used the word plane, just like the plane. And by this, they meant any figure that could be drawn using only circles and straight lines, which in their mind were ideal figures. So they didn't think of them as being produced as we would with a compass, for example. One should note that the Greeks actually knew other ways of constructing figures, and that in fact they classified the figures by the ways in which they could construct them. This classification divided figures into three classes. There were plane figures, which you see here. There were solid figures, which came up actually around the time of Euclid, and then beyond that point, notably in Apollonius, for example, where you could use straight lines, circles, and conic sections, parabolas, ellipses, and hyperbolas. And the reason they call that solid was, in their mind, those were shapes that were cut out of a cone, conic sections, and so they were solid in their mind. And then linear figures, and interestingly enough, I'm sure in Greek, I don't know in Greek, but certainly in French, linear in those days certainly did not mean a line, but a curve. So I'm thinking that the word probably just meant curved figures, which by then was anything they couldn't do by the first two methods. But by no means was every curve. They had specific curves that they thought about. Now, we're going to see that in a little while, that these latter constructions, as I mentioned, the non-planar ones, the solid and the linear ones, were viewed as mechanical. They viewed them as mechanicals, and they never used them in their proofs. So that was just a matter of drawing things. And Descartes was quite disturbed by the distinction that they drew, and I'm going to talk quite a bit about that. Now, what I'm going to do is show you, before I say that, one of the things I'm going to talk about today is the construction that the Greeks started to investigate as early as the time of the Pythagoreans. Now, the Pythagoreans were a century before the famous 5th century of Greece. They were already in the 6th century. And as my son tells me, they were almost viewed as some sort of a spiritual force by the time that the great playwrights wrote. And so they were very interested in constructing regular polygons, by which one means that all the sides and all the angles are equal. The Greeks invariably constructed them, if you think about it for a minute, by drawing a circle and cutting the circle in a certain number of equal arcs, and then they would just connect up the dots. In that process of circle division, literally in Greek, it just means the same words. It's called cyclotomy. So I'll be referring to that. Here's what the Greeks knew about. Actually, here's what the Pythagoreans knew about cyclotomy. So they knew you could draw a triangle, and again, you notice it's always drawn in a circle. So in other words, they could cut the circle into 3 parts. They knew you could cut the circle into 5 parts, so you could draw a pentagon. Using those two, they knew that you could cut the circle into 15 parts, whatever you want to call that shape. They knew you could draw a square, and they knew that you could, and finally, they knew that if you could divide the circle into any number of given parts, you could always double that number, because in fact you could bisect an angle, and that's all they really needed to do. So if you could do a triangle, for example, you could do a hexagon, and you could do a 12-sided figure or whatever from that fact. Okay, now as I said, this was all known by the Pythagoreans and was codified in Euclid, which was about 300 BC, and these pictures are from a modern version of Euclid's Elements that I believe is quite faithful actually to the original text as far as I can see. And the Greeks believed also that that was all you could do. They were quite certain. It's an interesting thing because in these days we have people trying to do all kinds of constructions and you have to explain to them that certain things can't be done. But it was actually quite the opposite with the Greeks. They were quite sure that that was the total number of polygons that could be constructed, and they went on and constructed others of them in solid and linear fashions. So it took until 1800, and it took the work of a 21-year-old man, Gauss, who showed the complete answer as to which polygons could be constructed and which couldn't. And what I want to talk about today, at least a little bit, is how that could have happened, because he was a very intelligent young person and obviously one of the great mathematicians. But you have to ask yourself, in those intervening years, you had all of the great Greek mathematicians. You had, of course, Archimedes. You had, as I mentioned, Apollonius. You had Romans who were very gifted at technical things. And then you had the great work of the Arabs, as we all know, who kept up mathematics. And not during that time at all did anyone discover this new thing that Gauss did. And so I want to talk a little bit about why that is and why it's not just a question of his great abilities, but something about the culture. And that's what I'll be talking about. So, in fact, let me turn exactly to that now. I should just put up the slide of Gauss's book. It's actually a wonderful book that we're all very happy to read. It is translated into English, and it's a beautiful piece of work. But who I really want to talk about now is Descartes. And basically, nothing at all was learned about even any kind of plane constructions. Pretty much, again, a little bit here and there, but pretty much from the time of the Pythagoreans, so you're talking about 6th century BC, until the time of Gauss, until the time of Descartes. And so let me tell you a little bit about this. This is 1637. That's actually a very nice picture. This is quite a remarkable book. What Gauss says, as you can see up here, and the title in French is on those problems that one can construct using only circles and straight lines. So it's exactly the question that the Greeks raised. And as you see, he says that all problems of geometry can easily be reduced to such terms that it's only necessary to know the lengths of certain straight lines in order to construct them. Now, of course, there'd be no way that any of us, if we didn't delve back into the past, would understand what this means. And it's very important and actually changed mathematics in certain significant ways. So let me tell you what he meant by this. And in order to do that, I'm going to show you just briefly a construction that was actually critical in the construction of the pentagon, which was very, very important to the Greeks. And I'm going to give you a rough idea of how it appeared in Euclid, and then I'm going to give you a rough idea of how Descartes would have done it. So, now the construction, and let me use this pointer here as best I can. There's a lot of lines in this picture, but the only line that's interesting ultimately is the line that goes from A to B. You see this line here. And the goal was, now this is what I need to explain to you because this is quite important. The goal was to cut this line at a certain point, and you notice what it says, so that the rectangle contained by the whole, that means all of AB, and one of the segments, let's say HB, the rectangle contained by, equals the square on the remaining segment. Now, it's a funny phrase, right? Because there's no rectangle that's contained in HB and AH. So what the Greeks meant, and again, they knew that they could do this by construction, was they would construct a rectangle with those sides, with HB and AB, which you, by the way, for the record, that's this triangle right here. Happens to be that same rectangle. And they were claiming that that rectangle had the same area as this square. Now, if you think about it, that's actually quite remarkable. I mean, it's a very obscure sort of thing to want to prove, and the fact that it could be used then to construct a regular pentagon seems even stranger, right? So I'm not going to give you the proof of what he did, but I'm just going to show you what the construction is, and I think you'll marvel along with me that anyone would have thought of it, frankly. So the idea is, and you can read along with me, is you take your line, you make the square on AB, which is this green thing, and then you have this line AC. This is all done with constructions. And you draw this line BE, which bisects AC. That's what you do. You then, which you can also do, extend. That's one of the axioms in Euclid. You extend this line, this vertical line right here, so that the length from EF is the same as the length from EB. And then you make this square that you have, and then you drop this vertical line. And where that crosses the line you started with is the point you want. That's remarkable, and the proof takes 2 or 3 pages and depends in essential ways on almost everything that came before it in Euclid. My own sense is that this was a kind of a cultural knowledge, that in fact it developed very slowly, and I want to get back to that point, is that I think, in fact, this is something that developed slowly and after all was codified 2 centuries later. So in my mind, this is basically some kind of cultural knowledge. Let me remark that what he's saying is that these 2 areas are equal, but Euclid had no way, or anybody else in those Greek times, or in fact anyone until Descartes, as far as anyone knows, had no way to think about measuring those 2 areas with square units. That's in fact one of the things that Descartes did. So the proof that the 2 areas had to be equal, these 2 areas here, this one here, the purple one, and then this green one, the proof that they would be equal is done by what we call congruence. They literally, as you see, they added this other rectangle to both of them and then proved that those were equal. So it was done by cutting up and adding different shapes until they got the same shape in the sense that you learned in high school with congruent triangles. So the point is that for them, areas were magnitudes. They were not numbers and couldn't be represented by numbers. They were primitive things. For example, the length of a segment is a magnitude, but you don't call it 2 inches. That would be what you would do if you were doing something besides mathematics. That was called logistics. The Greeks made the distinctions of numbers of things, which they call logistics, and numbers which was mathematics, and this was not numbers, this was magnitudes. It was a geometric concept. So you can see what the rules were that they had to follow, and you can see that probably it took them a long time to come up with this proof, which was just one step in a much longer proof. As I say, I think one feels that one's in the presence of some kind of cultural wisdom here, and I'd like to say a little bit more about that in a little while. Now let's look at how Descartes would have solved this problem, and this is actually, the next picture is up already. So we have the same picture here, but Descartes would have only interested himself in this line at the bottom. Okay. And Descartes would have used units. He would have simply decreed that the length AB was 1 unit. I'm going to show you in a minute how he justified that. But in his mind, he worked just as we would. He would decree that the line AB was 1 unit. Then in his language, he says, suppose the solution already affected. So he's making the assumption that there is an answer, which is already something that the Greeks, as you can see, would not have done. And he's saying, okay, that's the answer, AH, and let's call it some magnitude x. Well, then the other magnitude, of course, is 1 minus x. At this point, Descartes leaves the realm of geometry and does algebra. And that's the big change. And it's not because the Arabs brought algebra to the West. That's not the reason. The reason is because Descartes decided that you could use algebra in this context. That's the thing that's really quite remarkable. It's not that it was a tool. The tool of algebra had been around. People were solving fourth-degree equations by then. People knew about algebra. But nobody, until Descartes, decided to use algebra in this way. It's really, as far as I can tell, quite remarkable. So in any event, let me show you the next slide. Here's what he would do. But let's just remember what we're dealing with here. The square on AH is evidently x squared. And the rectangle on AB times BH is 1 minus x times 1. So that's what he would have done. He would have taken the formula on the top, which is exactly what you find in Euclid, more or less. He would simply put in his letters, and then he would solve it identically to the way we did, because they knew how to solve quadratic equations. So he come up with an answer. Now, I mean, that's not an answer that's acceptable to anybody. That's some kind of a quantity. You still have to answer the geometric question, which is, where is that point on the line AB? So the next thing he would do would be this. Unfortunately, I can't use this the way I was hoping to. He can construct this. Remember, we want the square root of 5 minus 1 over 2. He can construct the square root of 5 using the Pythagorean theorem. He can actually draw it, because he can take a triangle of length 1 and length 2. And again, he's got units. He doubles this unit, draws this line. He's got himself the square root of 5. He would literally lift it up, bring it over here, so that the total length of the line I'm showing you now is the square root of 5. And he would lay off on the right part here 1 unit. Well, evidently what's left is the square root of 5 minus 1. He would then take that square root of 5 minus 1 and bisect it, which he can do, giving him the square root of 5 minus 1 over 2. And he would then lay that on the line AB, getting his point. It's a very different argument, right? Much more efficient. So that's what Descartes would have done. However, this was new, and Descartes had to justify these arguments to his audience, who would have been skeptical. So let me just briefly show you what he did. And let me just get my sheet here and explain this to you. You see, the point is, as I was saying before, that there was no way in anyone's mind to multiply magnitudes. Let's say lengths. Lengths could not be multiplied. They were just lengths. You could multiply them by numbers, whole numbers. You could double them, triple them. You could multiply them by fractions. You could take half of a length. But you simply could not multiply together 2 lengths. Descartes had a certain amount of contempt for the fact that nobody had chosen to do it before him. And he proposed the following method of multiplying lengths. That's what you find in front of you, in fact. The first thing, so what he wants to do in this picture is he wants to multiply the length BD, if I get this thing, there it is, BD, by the length BE, which are arbitrary lengths. And to do it, he fixes himself a unit again, which is AB, and he draws this picture right here. Okay, so what he does is he's using the fact these should be, this thing works differently on every computer. You see these little squares? You should picture little dots, because that was what was on my computer, so I'm sorry about that. People don't like Bill Gates. I always used to like him, but it's starting to be where, he's starting to get to me. So what you know, as early as the mathematician Thales, who lived a century before the Pythagoreans, is that these are similar triangles, which means that the sides that I've labeled here, BA, BC, BD, and BE, are in proportion. And Euclid knew, again in the Elements, that in fact, if these sides BA, BC are in proportion with BD, BE, that in fact then the product, not the product, but the area contained in BC, BD, right here, would be equal to the area contained in BA, BE. So that was what was in Euclid, nothing about multiplication of lengths, but simply, again, if certain sides were in ratio, then certain areas were equal. That's what was in Euclid. Now, as you look, he set BA equal to 1, so in some formal sense, you can forget BA, and look what you have. It says BE equals BC times BD. And that was his definition. So in other words, what he wanted you to do was, if you wanted to multiply those two lengths, you would draw this picture, quite literally, and the result would be what you get. Notice that that definition has very little to do with the definition that we used back when we first learned multiplication, which was repeated addition. It's a definition that's basically based on area. I mean, it's hidden here, but basically it's saying that the product of two numbers is the number of square units in the rectangle that you build from those two numbers. That's really, in some sense, the only way we know how to define multiplication today. So it's quite remarkable that he did that, and it was very different at the time. Here, just so you see, is how, and we don't need to go through it, is how he would have explained to take the square root of a length, again geometrically, and come up with another length. You would have had to take the square root of an area to get a length normally, but here you're taking the square root of a length and coming up with another length. And that's what he means by reducing everything to lengths. That's exactly what he meant. Now, if you think about it for a minute, and Descartes knew this, from these constructions, and since he only cared about lengths now, not doing things like constructing triangles or squares or anything, he knew that if you could construct any given length, then you could, any given two lengths, you can construct their sum, their difference, their quotient, and their product. He also knew you could construct the square root of any length. So any process, as many times as you wanted, that just involved addition, subtraction, multiplication, division, and the taking of a square root. If you started with lengths you knew, you could construct any length you could get by that process. That was his great conclusion. And he believed, although he never proved, that those were the only lengths you could construct. Well, from there then, if you want to do something very sophisticated, you have turned your geometric question, and you see the labors that Euclid and his contemporaries and antecedents went to. You then turn a geometric question into a question of algebra, or in this case, number theory, arithmetic, in fact. And it's just a matter of time before somebody systematically develops the tools to describe certain lengths, because what we're talking about for regular polygons are cosines and sines. And cosines and sines of these angles satisfy certain polynomials, and from there you move forward. So this is what Gauss actually did. Gauss showed that, at least in the case of a polygon of 17 sides, that this line right here, so this length BC is one side of a 17-sided polygon. And Gauss could prove laboriously, but not with one bit of geometry, and indeed his book, Disquisitiones Arithmeticae, has no pictures in it anywhere. And it's interesting enough, he comments at the beginning of the section in which he does this remarkable result that he's just going to continue on to do arithmetic, but that the final result will surprise you, by which he means he's going to do this remarkable thing that he is quite proud to mention has been undiscovered for 1,000 years, which is really something, right? So what he does is, with some work, a lot of work, but work involving only numbers, no pictures, he shows that this length, 0a or OA, is actually this number, again, assuming that 0c is a unit. So we're assuming it's a circle whose radius is 1. And then you've got this very complicated formula. It doesn't matter how complicated the formula is. What matters is if you start somewhere, like right, let's say, over here, you can construct the square root of 17. We've just seen that. You can multiply it by 2. You can add 34, all by constructions. You can take another square root. As long as you don't see any cube roots here, or more complicated things like exponentials or something, as long as you only see square roots, you can do as much of this as you want, and with time you can construct the thing. Well, if you can construct 0a, you can certainly erect a perpendicular at a. We know that. And where it hits b is then the point that you connect from b to c to get the polygon. So that's what Gauss did. And he did that as a young man. As you see, basically, once the idea was set down by Descartes, it was a matter of time before somebody did it. He was a brilliant, brilliant person, but in fact, it was the idea that led to it. So just for your information, let me just tell you what Gauss actually said, because it's not too hard. So you notice the thing that's 17 is interesting. I mean, after all, among other things, you can't do 7, you can't do 11, you can't do 13, you can't do 9. What's special about 17 is that it's a prime number and that it's 1 more than a power of 2. It's 1 more than 16. And the 2 is because of square roots. That tells you in so many words that you can take square roots of square roots. So what Gauss showed is that the only prime-sided polygons you could construct were, in fact, what are called Fermat's primes, which are exactly what we're talking about, 1 more than a power of 2. And there are the first 5 of them. People believed that they were all prime. You see the big numbers very quickly, and the next one's enormous. But the next one up, the next one that could be prime, is in fact not a prime. And as far as anyone knows, those are the only ones. To this day, no one's gone any further than that. He showed that any polygon can be constructed by plane figures if, in fact, the number of its sides was a power of 2, we knew that already, times a product of these Fermat primes, all of them distinct. So I've given you a couple of examples. You could do 204 because it's a power of 2 times 3 times 17. But you can't do 7 because it's not a Fermat prime. And you can't do 9 because the prime is repeated. Even though it's a correct prime, you can't do it. So just so you can see what the result was. Now, this construction that Gauss did this enormous progress is by no means isolated. As you all know, in the years following La Géométrie, mathematics jumped forward at an enormous pace. There was Leibniz and Newton, who did their fundamental work on calculus. That was in the 1680s, 40 years later. And these ideas, applications of these ideas of physics, followed almost immediately. Euler, who was born in 1707, among other things, worked regularly with complex numbers. Those are numbers involving the square root of -1. Descartes was still uncomfortable with negative numbers. So that's less than 100 years after Descartes. And Gauss used these complex numbers, actually, in this proof. Although, as you notice in the example I gave you and in all the other ones, in the answer there are no complex numbers. But he felt perfectly comfortable to work with complex numbers to get this result ultimately about whole numbers or square roots of whole numbers. In the meanwhile, as you know, and this is really what I want to talk about for the rest of my talk, because mathematics developed at such an astonishing pace, all sorts of words that came into the language, borrowed from ordinary language at the time of calculus, just for one example, function, continuous, limit, words like that, had to be expropriated and given technical meaning in order to carry on the new work. There needed to be a vocabulary. You've seen it already with the word multiplication. I mean, Descartes already used the word very differently than anybody would have thought to use it, and in a very peculiar way when you think about it at the time, drawing yourself a picture of the sort he needed to do just to define what you meant by the product of two things. So this process went on for a long time, and leads me, just so you know, for the title of my talk, that's where the epsilon and delta come from, and I put up the famous proof, purposely putting it with no explanation because I expect nobody who's ever, unless you've had a couple of semesters of calculus and even more amazingly remember it, you're not going to know what this means. So I'm not even going to read it to you so much as to show you that, yes, there is an epsilon and there is a delta in there, and that, in fact, in some sense, our hardest task when we teach calculus is to persuade students that a definition of this sort, in fact, means what they think it means. In other words, they know the word limit. When you teach people with functions, they quickly understand physically, in some sense, what the limit of a function is. And to persuade someone that you need this definition to work with the intuitive idea in your head takes a lot of persuading. And that's exactly the sort of thing that has gone on more recently in modern mathematics. So it seems to me that we've gotten to a point where math and other disciplines are remote even from folks who are deeply motivated to learn them. If you look at your own disciplines and their histories, I wonder if you wouldn't agree with me. Take a look at music, for an example. In my mind, one could quibble, but the first truly great musical compositions to be produced by European composers were probably in the early years of the 18th century, a generation or two before Bach. Bach was, of course, about 40 years younger than Newton, so just to give you some idea that these are all things happening more or less at the same time. By the end of the 18th century, we passed, or Western music had passed, all the way through the classical period, pretty much, and counterpoint was over with. It was used, but I mean the period that was based largely on counterpoint died with Bach. So there were tremendous changes in music during that time. Beethoven, who I would observe because it somehow spiritually means something to me, is almost an exact contemporary of Gauss. And if you know Beethoven and you know Gauss, that's no surprise. It's somehow the beauty is very, very similar. But I note that, in fact, late Beethoven, the music he wrote at the end of his life, is a challenge even today to people who haven't spent a lot of time listening to Western music and getting prepared for the sounds that you hear. Much as Gauss's later work, in fact, is a challenge even to those of us who are professional mathematicians in many cases. And now, in some sense, 1 century later, not to quibble again, so by, say, 1920, I think European composers in their own minds, if you read the writings of Schoenberg, for example, had exhausted in their minds the creative possibilities in anything that would even be tonal, which is the only kind of music anyone had ever written up until that time in any culture. And so, in some sense, now we use the word modern for music that was written in 1920, which is almost 100 years ago, in some sense. And I think by modern, what we really mean is that even folks with innate great musical skills need substantial training to listen to it, just as they need substantial training to even contemplate mathematics these days. One thinks of the ancient words of Lao Tse, the square perfected has no corner, music perfected has no melody, love perfected has no climax, art perfected has no meaning. I will not speculate here on what it was to lead to these enormous changes in our culture at the time of Descartes, although I do have some thoughts about it. My son told me he would kill me if I said them. So, I would, however, like to talk a little more about Descartes, because I'd like you to consider some of the things that he said at the time that these changes were in the making. Interestingly enough, among Descartes' first interests was apparently astronomy. He knew Copernicus' work, which was about 100 years earlier. He knew it well. And he was also well aware of his contemporary, again, almost an exact contemporary, Galileo. And as you recall, Galileo had some trouble around those days, right? So Descartes was a devout Catholic. And if you read his letters, you see that, in fact, he believed that the church was not serious after 100 years after Galileo of attempting to repress the heliocentric view of the universe. In other words, the idea that the earth, in fact, went around the sun. And it came as a great shock to him, there were letters written on the subject, that Galileo's books had been burned. Descartes was at the point of writing a book on astronomy. He had it written and was about to publish it, called Le Monde, the World. And in fact, he never did. It was published after his death. And according to what he wrote to his friend, he was tempted to burn it. If you read people's writings recently, I think they're unfair to Descartes. They suggest that he was being expedient. But I don't think he was being expedient. If you read what he says, he was genuinely torn between his devout belief in Catholicism and what his senses told him. I think he was troubled. I mean, Galileo, as I understand it, was less troubled and very, very eager to make his point. But Descartes was troubled, and he never then returned to astronomy for the rest of his life. However, 5 years later, he published one of his works that we know very well, which I translate roughly as Discourse on the Method of Correctly Conducting One's Reason and Seeking Truth in the Sciences, which is a very abstract book. And interestingly enough, La Géométrie, which we've been discussing, appears as an appendix to that book. It's the only thing he wrote on mathematics, as far as I can tell, was that one appendix to this one book. And he makes an unmistakable allusion in part 5 of this book to his choice not to publish Le Monde. I mean, there's no way to miss this. And I'd like you to look at this because to me it's very significant. I'll read it to you. He says, further, to enable me to cast a bit of shade, he says ombrager, it's a little hard to say, but to shade over this variety of subjects, by which he means the stuff he could have gotten into trouble for, and to express my judgment regarding them with greater freedom, without being obliged to adopt or refute the opinions of the learned, I resolved to leave everyone here to their disputes and to speak only of what would happen in a new world if God were now to create somewhere in the imaginary spaces matter sufficiently to compose one, and were to agitate variously and confusedly the different parts of this matter, so that there resulted a chaos as disordered as the poets ever feigned, and after that did nothing more than lend his ordinary concurrence to nature, and allow her to act in concordance with the laws that he had established. So it seems to me that Descartes had been put in a position where it was almost impossible for him to recognize his deeply felt religious knowledge with the knowledge he had obtained by being in this world, knowledge that was built on the evidence of his senses, because what else is astronomy but a series of deductions built on careful observation? To continue to contemplate this latter knowledge, he felt the need to view it as happening somewhere else, in a place that God had abandoned, allowing things to develop without the benefit of his presence. In effect, he felt the need to leave the spiritual community in order to pursue science. It seems to me that this choice is also reflected in what he says about the Greeks in La Géométrie. So let me show you some quotes because they're all apropos. And I've left you the French. Interestingly enough, I read this originally in French not knowing that there was a translation. And it's funny, one learns when one does this thing, something that you all know in the humanities, but that I certainly didn't know, that it really is good to read it in the original language because the translations are sometimes not what they should be, I think. So I just put what I think is translation here. Those of you who know your French from that period better than I will perhaps quibble, but I thought I'd show you them both up at the same time. He's talking about, he's writing this in about the 7th or 8th page of this book, where he wants to tell you about what he thinks the Greeks would have thought of what he had just done, the very thing we talked about of reducing things to lengths. And he says, I don't believe that the ancients had noticed my approach I put in, because otherwise they would not have taken the trouble to write so many fat books. You see it's up there, it's gross, fat books on the subject, in which the very order of their propositions lets us know that they had no real method for finding everything, but that they collected only those things which they met up with. Now, if you know Euclid, that's a remarkable assertion. And he knew Euclid well. I mean, the unspoken assumption is that if the Greeks had come upon Descartes' ideas that all geometry could be reduced to the length of certain lines, that they would have embraced that idea and done as he did. Yet, as I said, the major tool that Descartes used was known to Thales before the Pythagoreans, and I don't really feel that it seems like rocket science to decide to fix a unit. So I think it's more likely that, as I said earlier, the Greeks viewed their mathematics as some kind of communal wisdom, and that they had no desire to go in certain directions where they could have easily gone. To me, one could as readily say that the ancient Hebrews didn't understand theology because their holy book was not systematic, but rather was just a collection of stories. I also think that Descartes needed, for some reason or another, as we've seen, to distance himself from these ancient traditions. And I think here's another example, and I mentioned this before. Here's his comments on the Greek classification into plane, solid, and linear. So he says, in addition to that, in other words, he understands what they did, but he said, it astonishes me that they did not, in addition to that, distinguish various degrees among these more complicated curves, and I do not know how to understand why they have named them mechanical rather than geometric, since to say that they are mechanical because it is necessary to use some mechanical device to describe them would rule out for the same reason circles and straight lines. Well, it's hard to think that he would really be astonished by that. He had read Euclid, he had certainly read Aristotle very well, and he knew that the Greeks viewed circle and lines, for better or worse, whether they were right or wrong, as ideal figures, and he viewed these other things as things that you created somehow physically. As my son pointed out, it would be very much the same as if a journalism today was quoted as saying that he refused to use word processors because he only felt right when he was using a typewriter. And someone 1,000 years from now, knowing full well what that was all about, said, well, I mean, come on, isn't a typewriter a kind of a word processor? I mean, people make cultural distinctions. And what I think is that these questions, these passages in Descartes, I think reflect a trend, in fact, several trends in the European intellectual tradition that are still with us today. I've already remarked on the first one of these, as I've just shown you, which is the apparent need to destroy shared tradition and to reinvent the culture regularly. And this trend, I believe, has accelerated lately. To describe the second trend, I'm going to turn again to my friend and colleague, Gene Madison, who's always a rich source of traditional wisdom. And I'm going to tell you one of his stories, one of his many stories. He said that he had a conversation some time ago with a colleague in the math sciences on some books that were current at the time and that purported to give statistical proofs that African Americans were simply born less intelligent than white folks. This colleague said that he had found these works interesting, and he wondered what Gene thought about them. Gene always wanted to give anyone the benefit of the doubt, and therefore never assuming, in spite of the overwhelming evidence in front of him, that it was actually white folks who were in fact born with a deficit of intelligence, tried for some time to reason with his colleague. But after a while, Gene got tired of the discussion, and he simply said, look, anyone who believes what these folks do is just anti-black. His colleague was disturbed by this and said, no, they're not anti-black, they're just pro-knowledge. So I like to talk about pro-knowledge a little bit because I think that's the second trend in our culture. At its best, it's led to remarkable advances in what we know about the world. Einstein, for example, modified Newtonian physics by throwing away the axiom that the physical world is Euclidean, an axiom that up till that time seemed so obvious that it was taken entirely for granted. As Gene's colleague would have put it, Einstein wasn't anti-Euclid or anti-Newton, he was just pro-knowledge. But at its worst, the pro-knowledge approach, the pro-knowledge point of view of European culture has led to some of the most horrifying and unhuman acts in the history of the world. Just as no prior culture has ever understood relativity, no prior culture has had scientific theories of race and of theories that have justified slavery and genocide, just as surely as we've had other theories that have increased our lifespan and, at least for some of us, enhanced our lifestyle. I think that a third trend that began at the time of Descartes is the belief that knowledge in our culture that knowledge that our culture brings to the table is better in some ways and that other folks need to assimilate to us. We have standard tests which are designed to tell us who will succeed at our universities. And let's even grant that they're good for that. Let's suppose they do tell us who succeeds. On the other hand, we know these tests to be culturally biased. Isn't this just the academic version of the well-known expression, my way or the highway? I do not say these things to cast judgment on the culture that we have inherited from our European brethren, but rather to speculate on what our future will be if these trends continue unaltered. As I have remarked, the European tradition has failed to produce a single piece of music that has anything approaching wide appeal for nearly 100 years. Mathematics and the other sciences have become more and more difficult to understand, even by people with substantial training in these subjects, and they are often pursued in a lonely fashion. I don't think that we can expect folks to continue to pay the higher and higher price in time and frustration necessary to assimilate to our academic culture, especially when it is at a culture that more and more cannot explain clearly what the rewards are for this enormous time and effort, and in addition, so often fails to respect the cultures that these folks come from, whether they are African American and Latinos, or they're from the traditional culture of our own state and region. As we are measuring them with our standard tests, they are measuring us as well, measuring our pro-knowledge tradition in other and perhaps more fundamental ways. As my colleague Floyd Williams is fond of saying, they won't care that you know until they know that you care. So it seems that our American intellectual institutions are at a crossroads. We can continue on the path I have outlined, a path that will lead us further and further from the center of our society until ultimately we risk marginalization. Or we can change that path. But we cannot change that path from inside the academy. That has been tried before and it hasn't worked. It is good that we are becoming interdisciplinary, but what we need to become is extra-disciplinary. To embrace this new multilingual, multi-ethnic culture with its music and poetry and great spirituality that is growing up around us, and ask of this new culture whether we might be permitted bringing our great gifts with us to assimilate into it. To leave, as Descartes said, everyone here, to their disputes, and to speak now of what can happen in our new world. We need never fear that we will vanish into this new culture, for this new culture has a great respect for tradition, ours and others, and the same great sense of spiritual wholeness that can be found in any culture based on tradition and community, including the culture that gave us Euclid and the other works of antiquity. They will slow us down and ask for explanations, and they will help us to know what is worth preserving and what is not. We know this in the math department, and if you look around you today, you will see our students among you. Students from every corner of America, from Latino serving institutions and historically black colleges and universities, as well as from the great colleges and universities of our own state and region, from North Carolina and Puerto Rico, and from just down the road. We have not asked them to assimilate to us, although we are eager to teach them what we know, and they are eager to learn. Rather, I think we are assimilating together and building a community. The start of this occasion was blessed with a beautiful performance of the music of Robert Schumann, one of the great and one of the many great and precious gifts that European culture has given the world. So I think it will only be appropriate to end this occasion with two songs from the blues tradition, and I bring you Tony Brown for that reason. Have a great evening, and thank you for listening.
Well, it was completely mind-boggling. It made me think of too many things. It also made me think of oneness. All things that are engulfed in the terminology oneness have been so divided that we feel we're different. How the universe can be divided in so many different manners and forget the existence of love. It's amazing.
All they wanna hear is down got to